So we are studying about planar graph. When a planar graph is embedded on plane, we have this plane multigraph, plane graph. And once it's given, we have vertices and edges as well as faces. And we have defined these faces. And using this concept of dual graph, we show that there are relations between the lengths of faces, which is the number of edges on its boundary, and the number of edges in graph. And now we have these three objects in this plane multigraph: vertices, edges, and faces. And they satisfy the following relation, which is known as Euler's formula. So, if connected graph, the connected plane multigraph, G as say P vertices, E edges, and F bases, then P minus E plus F equals 2. Here, we consider multigraph as multiple edges. If it makes difference whether there are multiple edges or not. So each edge gets mapped to the curve, and then each loop also maps to this closed curve, which gives us additional faces. So this is well-known Euler's formula, and proof is not difficult. We can prove this using induction. Induction on number of vertices. If P is 1, then what? If there are only one vertices, then you only have E loops and E plus 1 faces. So, if you have 3 loops, you have 4 faces. It proves the base case. If E is bigger than 1, if this G is connected, it has a edge which is not a loop. So it has an edge. Then what we do is we contract this. We contract this edge. Then what we have? This contraction is it's an operation which were motivated from this plane multigraph. In this plane drawing, the drawing of a graph, plane embedding, what we can consider is that when there are these, we take this curve, which is called we take this edge, and then we can shrink it. We can redraw it by moving both vertices in this direction. And while doing that, these other edges also continuously move. And then we do this until they collide to one vertex. Okay, so in this contraction, let's assume that in this time, this contraction actually consider the way that the multiple edges may arise. We contract this edge in a sense that if there are two edges, one standing here, one standing here, and now we have two. Then if there was like two here and one here, then we have three edges between. So we can consider such a contraction. In such a contraction, it yields another plane multigraph. As I mentioned here, it's clear that we can shrink it continuously so that the other edges also moves continuously. And while doing that, we don't introduce any new crossing. And the resulting graph is a plane multigraph. And this is a plane multigraph, a G prime, with D minus 1 vertices and E minus 1 edges. Only this edge disappeared. Other edges are here or there. And the number of faces does not change. And F base. Why? If you consider this contraction, all the faces which does not contain this edge on its boundary, they are still there. We just continuously move its boundary. It's never disappearing. And the faces which have this edge as a boundary, it's just while we are contracting it, the length of this space just shrink by 1. But again, it doesn't disappear. Of course, it doesn't produce a new face as well. Here what? We merely shorten boundary, but it may create loops and multiple edges. Okay, maybe let me put the parenthesis because it's not really relevant to the group. But anyway, so the point is that the number of vertices and edges decreased by 1, but the number of faces stayed. And by the induction hypothesis, what do we know? E minus 1 minus E minus 1 plus F is 2. And that implies that P minus E plus F is 2. So we can prove this Euler formula. And using this Euler formula, we can derive some relationship between number of vertices and number of edges in planogram. So let G be on a planogram, which is n-vertex planogram with the m edges. Then here it's planograph, not plane graph, so we don't have any faces here. We only have vertices and edges. And if n is at least 3, then what we have is that the number of edges is almost 3n minus 6. So here this is graph, not vertigraph. And if also G is triangle free, then we get a better upper bound that m is in most 2n minus 4. How do we prove this? First, it's sufficient to prove for connected graph. Otherwise, as we can add an edge. If graph is not connected, you add an edge between components, then you get a connected graph. And if you prove inequality for that graph, then original graph has less number of edges, so it's automatically proved. So consider some planar embedding of G, and let F be the number of bases in some embedding of G, some planar embedding of G. And now what? We know that this is the graph, not multigraph. That means there is no loop or no multiple edges. And every face has a so the only case that the face is enclosed by one edge or two edges are if there are loop or multiple edges. So every face boundary in a connected plane graph at length at least 3, so that Fi is the list of this face length. And what do we know? From the handshake lemma on its dual, twice the number of edges is same as F, sum of Fi, then this is at least 3F. Because there are F many faces, and those as length Fi, then you sum all of them, and there are at least F numbers, all of them at least 3, so it's at least 3F. And what do we have? From the Euler's formula, B minus E plus F is 2, so n vertex M edge F faces is 2. So what do we have? This is what? At least 3 over 2m. No, sorry. F is at least m mod 3 over 2m. Sorry. So where was I? Okay, so this we know. So let's write it this way. 2 is that, and then here what is it? N minus m plus F is m mod 2 over 3m. It's n minus 1 over 3m. This shows that m is m mod 3n minus 6 as this side. And if G is triangle free, then what do we get? We have the same proof, but here, instead of 3F, we have 4F. Because each faces have length not 3, so it's at least 4. Then again, what do we get? We have this, and then you just do the computation, then you get this. And this now gives us the new proof on the non-planarity of K5 and K3. If you have K5, then how many vertices do you have? 5 vertices. How many edges do you have? 10. And what? If 10 is bigger than 9, which is 3 times 5 minus 6. So K5 is non-plan. If this is planar, then this inequality has to satisfy, but it didn't. It did not. So this is not planar. How about K33? N is 6, M is 9. But this is bipartite graph, so it's triangle free. So this relation has to satisfy. But what 10 is bigger than 8, which is 2 times 6 minus 4. So K33 is not planar. So this Euler formula provides a simple proof that these are not planar. Okay, before moving into, study about the complete characterization of planar graph. So remember our main goal that I mentioned before is to decide whether a given graph is planar or not. We want to find the good characterization of the planar graph. But before that, let me define one concept. A multigraph is outerplanar if it has an embedding with every vertex on the boundary of the unbounded space. So in this embedding, you have unique space which is unbounded, and then if on that boundary, every vertex is on that boundary, then we say that the graph is outerplanar, and we say that outer plane embedding. Outer plane multigraph is such an embedding. Then with this, we can show that K4 and K2, 3 are planar, but not outer planar. Okay. So the proof of it is not difficult. Being planar, you can just find the one way to embed. Then it's easy. But for outer planar, what? In order to be an outer planar, you have to have a spanning cycle bar, which would form a boundary of the outer, boundary of unbounded space. Okay, to be specific, these are two connected graphs. So in two connected graphs, you consider the boundary of a base, then that has to be a cycle, not just like any closed work. So, if this is outer planar, then that base has to be the base, unbounded base, its boundary has to be a cycle, which is spanning cycle. But this does not have a spanning cycle, so this is not outer planar. And here, this has a spanning cycle. K4 has spanning cycle, but in that case, you have two additional chords. Both of them have to be inside of this spanning cycle. If one is outside, then it's not outer plane embedding. But in that case, it's contradicting each other. It's conflicting, so you cannot put them. So they are not outer plane. So, okay, so we learned about this Euler formula, and then the concept of outerplanarity. And in next video, we will learn about the theorem which completely characterizes the planar graph.